Every day, engineers and planners open up Excel to design multi-million-dollar business systems. And almost every time, they build the entire foundation of those massive factories on simple average numbers. On paper, the logic is flawless. Machine A builds an average of 10 parts an hour. Machine B processes an average of 10 parts an hour. Therefore, the total system will output exactly 10 parts an hour. But if you build that exact factory in the real world, you will only produce about 7 parts an hour, and your company will rapidly bleed cash. This mathematical paradox, where perfectly logical averages completely fail in reality, is known as the Flaw of Averages. Today, I'm going to show you exactly why static spreadsheet numbers lie to you, and how engineers use a casino trick to accurately predict the future instead. Using static averages to plan a dynamic system hides the specific risks that lead to systemic breakdown. Let's look at the hard logic. Why doesn't the seemingly perfect math of 10 equal an actual real-world output of 10? The culprit is variance. Machines aren't perfect, and their performance fluctuates hour by hour. Imagine hour 1. Machine A experiences a minor jam and outputs only 8 parts. Machine B is running perfectly and is ready to process 12 parts, but it only receives a stream of 8. Because it is starved of parts, Machine B is forced to sit idle. Those empty slots on the conveyor belt represent extra processing capacity that is now permanently lost. In hour 2, the exact opposite happens. Machine A runs fast and pumps out 12 parts, but Machine B has a slight delay and can only process 8. All those extra parts violently pile up as a bottleneck on the belt. Variance constantly forces interconnected systems to be either starved of parts or choked by inventory. That is how an assumed 100% efficiency on paper degrades into a brutal 70% reality. To properly plan a factory, we have to abandon single numbers entirely and instead start dealing in probability. We stop defining machine cycle times as a static 5 minutes. Instead, we define reality as a range, a minimum of 4 minutes, a maximum of 8 minutes, but most likely 5 minutes. This visualizes as a probability curve. We then force the computer to pull a random number from this exact curve for each machine to see what actually happens. By replacing single averages with probability distributions, we stop pretending the world is perfect and finally start measuring its actual chaos. But rolling the dice just once tells you absolutely nothing about the long-term future of a factory. To see the real picture, we use the Monte Carlo Simulation, a mathematical method designed to play out every possible future timeline. This graph visualizes the software running the factory for an entire year, resetting and then running it again 10,000 times in a matter of seconds. Every single run uses slightly different, randomized cycle times. The software mathematically brute forces the chaos of the real world, testing thousands of randomized cycle times to find the points of failure. This statistical map reveals exactly where, when, and how the system will break under pressure. We can apply this simulation power to massive real-world financial decisions, like calculating safety stock, the exact backup inventory required to ensure a factory never runs out of parts. Relying on averages leads to ordering too little and shutting down your factory, but panicking leads to over-ordering, wasting millions of dollars in warehouse costs. By isolating the extreme right edge of this statistical heat map, Monte Carlo outputs a surgical requirement. It looks at those 10,000 futures and tells you that to guarantee a 99% success rate, you need exactly 412 backup parts. Not 400, not 500. Averages belong in textbooks. Survival in the real world requires simulating the chaos to cut your inventory costs to the absolute bone with zero risk. Monte Carlo Simulation calculates exactly how many parts you need, but deciding exactly where to geographically build that warehouse requires a completely different operations research equation called the center of gravity method. Click the next video to see how it pinpoints facility locations to the exact GPS coordinate.